So now at this point, you should be very comfortable with the differentiation of the inverse trigonometric functions. And we need to move on to now integration, just going backwards. And so you know that the derivatives of the 6 trigonometric functions have a pattern to them in that 3 of them are the negative of the other 3, and those 3 are the co-functions. And if we're going to go backwards, what we realize is that we don't actually need to talk about all 6 inverse trigonometric functions. So if you think about it, 1 over the square root of 1 minus x squared is the derivative of arcsine. And so that could go back to the arcsine. Okay? And negative 1 over the square root of 1 minus x squared is the derivative of arc cosine. And therefore could go back to the arc cosine. When I say go back, I'm basically saying that if I integrate each one of these, the integral of each one should equal the arc sine and the arc cosine. However, if I looked at the negative arc sine, and I said, what's the derivative of the negative arc sine? Well, it should just be negative of this, which is exactly here. So technically, I could say that the integral of the negative 1 over square root of 1 minus x squared is equal to arc cosine x, but it could easily just be the negative of the arc sine. And by doing this, what that tells me is that I really don't need to think about 3 of the trigonometric functions when it comes to integration in terms of going back to those inverse trigonometric functions. So we really only focus on the positive ones. Okay? So those positive ones were arcsine, arctan, which would have been 1 over 1 plus x squared, and arcsecant, which would have been 1 over absolute value of x, square root of x squared minus 1. Now, I only use the basic ones. I didn't use the u ones, okay? So this one goes back to arctan, and this one goes back to arcsecant. Now again, that's only if it was x, right? Arcsecant of x, arctangent of x. But we saw that lots of times you're not going to take the arctan of just x or the arcsecant of just x and do the derivative of that and go this way. Okay? So in that case, we need to expand on the integration component. If we're going to integrate this side, we need to look at this in a little bit more general format instead of just going straight to arctan. What if we have to go back to arctan of 3x or arctan of 3x plus 2 like we took the derivative of? And so that's where these derivative rules are going to come into play. Essentially, using the integration version of the chain rule, which is substitution. And so we look at each one of these. So let's look at first arcsine. So in this, u is a function of x, and a is a constant. Specifically a constant greater than 0, so a positive constant. And so now what we have is we have this, in that if I look at it a little bit bigger, du over the square root of a squared minus u squared equals arcsine of u over a plus c. And so a is a constant, right? So this a here would be a constant, and that's the same a there. And whatever this function of x is here, the derivative of that function should also be here, and that is going to be the u. Okay? So it's almost like the u prime we were looking at. That's really what this du stands for, right? So to see that this really works, the easiest way to check to see if an integral is true is to differentiate, right? So if I differentiate this side, I should get this side. So let's take a quick look at that. I'm not going to do it for all of them, because once you see that it works for one, you'll realize that it works for the other ones. So if I looked at arcsine of u over a. And I said, let's take the derivative of this thing, okay? So let's take the derivative of this thing with respect to x, because remember, use a function of x, so I'm going to do it with respect to x. I'm going to use my derivative rule for arcsine, which again, you should be familiar with. And so that's going to be u prime. So this whole thing is really your u now, it's the thing inside there. So the derivative of that would just be 1 over a, sorry, it would be, my mistake, it would be u prime over a over the square root of 1 minus u over a squared. Well, that's not quite what we see here, okay, but we'll get there. So I'm going to write this as u prime over a, this is in the denominator, so I'm going to bring it down here, 1 minus u squared over a squared. I'm then going to write this as a single fraction, so common denominator of a squared, so we have a squared over a squared. So then I'm going to write that as u prime over a times the square root of a squared minus u squared all over a squared. Now, since this whole thing is in the square root, I'll take the square root of the numerator and the denominator, but when I do that, the square root of a squared would just give me a, therefore u prime over a square root of a squared minus u squared over a, these cancel, and you see you get u prime over the square root of a squared minus u squared. U prime is basically the du, and that's where you see this happening. So then if I integrated this, I get back to this. So this gives us a little bit more general integral to do, because otherwise, if we didn't have this, the only integral we could do would be the integral of 1 over the square root of 1 minus x squared dx. The whole idea here is that this doesn't have to always just be a 1 as the constant. It could be any constant, and we could still make this work. And this isn't just an x, it could be a function of x, and we could still make this work. Okay, so we can still get this arcsine to give us the answer. So there's your integral. And again, we're not going to worry about the arc cosine, because if I just put a negative in here, you could say, well, then it's arc cosine here. But I could also just say that it's the negative of the arc sine, which is a lot easier. It cuts down the amount of integration rules I need to remember. Here's your arctan integral. Here's your arcsecant integral. Okay, all basically taking the same pattern. This should look familiar to you for the arctan derivative, a little bit tweaked, but should look similar to the arctan derivative. So it's 1 over a, arctan u over a. And again, this should look similar to you for the arcsecant. Normally there's an absolute value here, but instead we put the absolute value in the answer here. So here we do some examples. And the key to integration is recognition. Is what does this integral look like it takes the form of? Okay? Clearly, integration is harder than differentiation. It always is, and it always will be. But the way you can make it easier in yourself is recognizing patterns of certain types of integrals and what form they have. And that only works if you memorize your basic integration rules. So anyway, we need to recognize that this integral right here has a pattern very similar to the arcsine. So let's see if we can make that work. And sometimes you think that it has a particular pattern to it that doesn't quite work out. So you can't just force it to work. Well, let's see what we get here. So if we said, all right, a equals 3, and u equaled x, and then du would be the derivative of x, so that would be dx. And I put all those things into this integral with a substitution. Well, I would have du, that's dx, over the square root of 9, which is 3 squared, so a squared minus u squared, because x is u. Well, that looks exactly like that. So then the answer should be arcsine of u over a plus c, where a and u were 3 and x. So arcsine of x over 3 plus c. And that's it, right? But the key was recognizing the form. Okay. If you're not sure you got the answer right, you can always differentiate your answer, and this should bring you right back to here. We're not going to do that, and you can do that to check if you like in the future, but we're going to move on. So here again, pattern recognition. This has a pattern similar to the arctan. And one reason that kind of sticks out to me is there's no square root down here. Both the arcsine and the arctangent, the arcsine and the arcsecant have that square root in the denominator. The difference between those is a little bit of subtraction. And maybe this doesn't work out to be exactly what you think it is, but this one will. If I let a equal the square root of 5, and I do that so that this becomes a squared, and I let u equal 4x, and again, that's so that this becomes u squared. The derivative of u should be 4 dx. Now, all this is good, but I don't have a 4 dx. Well, that's where your trick for substitution comes in, where you remember, well, I could just move this by dividing it, and so I can swap the dx for a du over 4. So what do I end up with? I end up with the integral of dx, but dx is du over 4, so the over 4 I'm going to pull out to the front with this constant multiple. Just makes things a little bit easier. And then I get 5, which is a squared, because a was the square root of 5, plus 16x squared is u squared. Well, that's exactly what we're looking at here. So this should be 1/4, because it's a constant multiple, times the integral. Well, the integral should be 1 over a arctan of u over a plus c. Again, where a was square root of 5 and u was 4x, I get 1/4 times 1 over the square root of 5 arctan of 4x over the square root of 5 plus c. Now this square root of 5 in the denominator here and here, totally fine. You can just leave it. I'll write this as 4 square root of 5, just to make it look nicer. Arctan of 4x over square root of 5. That whole thing's inside the arctan, so you want to throw some parentheses around just so you remember, that's fine, plus c. But you could rationalize this. If you want to rationalize this denominator and this denominator, go for it. Not necessarily. You're usually not going to see it rationalized at this point. So leave it. All right, here we go again. Pattern recognition, realizing that this denominator takes the form of what the denominator of the arcsecant looks like. One big key here is this subtraction. You know that you have these two square roots. You have u squared minus a squared, and you have a squared minus u squared. In the denominators, make sure you tell the difference between your u's and your a's. This is a u. In that, this one is what we need for the square root in the denominator for arcsecant. This is the one we need for arcsine. That makes a difference because a is the constant, u is the function of x, and order of subtraction matters. So that's a pretty important part to this. So recognizing we kind of have everything that lines up with arcsecant, we can see, all right, how can we make this work? So if we let a equal 3, that would give us a squared. Then u equals 2x, there's u squared. So the derivative would be 2 dx. Now we don't have an extra 2 sitting around, so we'll just divide by the 2. And remember, this x is going to have to come out too, because all the x's have to be swapped out for u's. So that's just coming from here. We would say u over 2 equals x. That's just moving this 2 to the other side by dividing. And what we come up with is the integral of dx, but dx is du over 2, so the du over 2, I'll pull the over 2 out to the front as a constant multiple, x, which is u over 2, times the square root of u squared plus a squared. And so we're generally at this point, but this u over 2 is the only thing. Well, this is a fraction. It's a fraction in the denominator of another fraction, so what do? You divide by a fraction, you flip and multiply. Well, if I flip this over, this 2 actually would come up here. Let's put it in red, come up here. And so now these two 2's will cancel. So this 2 went here, and then I canceled these 2's. So what do I end up with? I end up with du over u square root of u squared minus a squared. I don't know why there's a plus there. This right here should be a minus. And that's exactly what I have here. So my answer should be 1 over a arcsecant of the absolute value of u over a plus c. Again, make sure you know the difference between your u's and your a's. A was 3, so 1/3 arcsecant of the absolute value of 2x over 3 plus c. And this absolute value is important. I have to leave it there because 2x could be negative or positive depending on what x is, so that absolute value is critical. That absolute value really comes because of the absolute value in the derivative formula, but there's your answer. So pretty simple as long as you recognize the pattern. But we all know integration is never, or I shouldn't say never, is not always that simple. So here's an example that gets a little bit harder. So we're looking at this integral, looking at the setup of the square root. Your thought should send you to the integral of dx over u square root of u squared minus a squared, which is your 1 over a arcsecant of the absolute value of u over a plus c. It should send you there. The reason being the order in the subtraction. I think the first guess a lot of people give me when I ask this in a classroom is arcsine. And they think, well, this looks a lot like this integral. Du over, it should be u here, du over the square root of a squared minus u squared. Mainly because there's nothing outside the square root, which is what you need for arcsine, so that's why this is a problem. But the problem with using arcsine, which is this one, this would be your arcsine of u over a, is the order's all wrong. This is a squared minus u squared. It's a constant minus the function of x. You don't have that here. So this is off the bat. This is out right away. This would be the only one that looks close, but again, we're missing something, right? But at least the order's right. So if we're going to try this, we need to see, can we make this happen? Well, we can. Sometimes you can't, right? In this case, we can. And you don't know until you try. Sometimes you try something you think might work, and it doesn't work. It's fine. Go back. Say, well, what else could I do? What else does this look like? What other options do I have? We're learning all these different tricks and techniques we can come across to get this integration to work out. So right now, we have some inverse trig integrals we can try. So what I'm going to do is I'm going to start by saying a equals 1. So there's a squared. U is going to be e to the x. Now the reason why that is because e to the x squared is a power to a power, and I should multiply those together, so e to the 2x. And so this is now u squared. So now I got u squared minus a squared. If that's the case, then du should be the derivative of e to the x, which is e to the x dx. Right. So we have a couple of problems here. We don't have an extra e to the x sitting here with this dx. And what I'm going to do is something we normally don't do. We normally don't take a function of x from this side and divide it over to the u side of the equation. If it's a constant, yes, we've done that a bunch of times, but usually not a function of x. But I'm going to do it here. The reason why I'm going to do it here is because it's not really a function of x in the long term. Yes, it is right now. This is an e to the x, and this is a du, and I really don't want x's and u's mixed together here. But remember, e to the x, we said, equals u. So I could say this is just du over u. Okay? So dx equals du over u, and that's where that extra u comes in. So what do I have? I have dx equals du over u, and I'm not going to pull that out to the front like I've done with a couple of the constants, because this isn't a constant multiple that could come out to the front. It's a u. It's a variable for which I'm integrating with. Then I have the square root of u squared minus a squared, and now I have everything I need for arcsecant to work out. And again, that's not always going to work out to your benefit, but at least having an idea of this could turn into an arcsecant because I have a pattern like this. Let me try it out. And don't be afraid of trying something. Sometimes it doesn't work. Making mistakes is where you're going to learn the most. And trial and error. And realizing what works and what doesn't. The more that you do, the better you get. All right, so what do we get here? We get 1 over a arcsecant of absolute value of u over a plus c. So a was 1, so this just becomes 1. I'm not going to write it. Arcsecant of absolute value of u e to the x over 1. Again, not going to write the over 1 plus c. Now in this case, e to the x is always positive. So I really don't need these absolute values, so I'll finalize this by saying the answer is really just arcsecant of e to the x plus c. If you can simplify it, drop off those absolute values, you should do it. I mean, if you didn't, it's not the end of the world, it's still correct, but it's simpler if you can drop the absolute values. Okay, so we're going to take a little side street here before we get back into calculus. Completing the square. Completing the square is a method of solving quadratic equations that you would have learned all the way back in algebra. You didn't just use it to solve quadratic equations, however. You would have used it to find the vertex form of a parabola. You could have used it to rewrite the standard equations of a circle, of an ellipse, of a hyperbola. Use it for a lot of things is the whole point. It is not just used to solve quadratic equations, and in fact we're going to need it for calculus too. It's a way of manipulating a quadratic and writing it in a different form that uses squares, essentially. And so this is your basic completing the square setup, in that if you had, say, a quadratic trinomial, say something like this, it doesn't even have to be a trinomial. If you just have these first two terms here, the c is almost irrelevant to this whole thing. We can use the method of completing the square to rewrite this. And the way we do that is all about this term right here, this b component to the linear coefficient. One trick to this, and the reason why this works, is really the coefficient of the x squared. The coefficient of the x squared has to be a 1. And if the coefficient of the x squared is a 1, then we look at the linear coefficient. If it's not a 1, you got to make it a 1 first. Okay. So once we do that, we look at that b. And what happens is if we take whatever that linear coefficient is, divide it by 2 and square it. And we add that into this polynomial. Now you can't just do that because you feel like doing it. We also would subtract that out as well, so they cancel each other out. But we look at, let me erase some of this. We look at this much here. What happened is we just created a polynomial in this component right here that is factorable. And it's factorable as this, okay? X plus b over 2 squared. We still have all these other pieces, which is really just one giant constant when you think about it. B is a constant, b over 2 squared, and c is also a constant. So this altogether is one constant that we would have over here, but the crux of the matter is basically sitting right here. And it's just, we created a factorable polynomial. And it all stems from this basic binomial squared multiplication, which you've done tons of times. You have a plus b squared, it's a squared plus 2ab plus b squared. And essentially by creating, and maybe I should probably use different variables here. So let's use, say, u and v. So this would be u squared 2uv, and let's say v squared. Essentially what you're doing is you're saying, I started off with this, and if I create this piece on the end, then this whole thing can be factored like this. And in this thing above, and in what we're looking at above, essentially, here is my u, and b over 2 is my v, so that's why you get u plus v squared as the binomial. So let's just say, for instance, I gave you x squared plus 4x plus 7. And we had to apply completing the square, say, to this. Again, this is the c. Let's just ignore that. Look at this piece right here. You have a 1 as your x squared in front of your x squared. There's your b. So if I only have to put an arrow, I can just say equals. If I look at this x squared plus 4x, and I added this divided by 2, which would be 2, squared, I also would have to subtract that as well. I still have the plus 7 sitting over here as well, but nonetheless, this is the b over 2, the b over 2 that we were talking about, okay? Then this much of this polynomial can be written as x plus 2 squared. Now this is what's left over, which in this case is negative 4 plus 7, so what's that going to give me? 3. But this here is the same as this here. It's another way of rewriting that polynomial using a square component, and it combines the two x pieces into one square. A lot of people look at this and they go, oh, well, when you went from here to here, where did the 4 go? The 4 is there, it's just factored into this piece. If you were to multiply this out, again, using maybe something like this, you would see the 4 come back again. You should be familiar with this. This should be nothing new. If you need some help with completing the square to review this, I would suggest you could look at, I have videos on my channel in completing the square. You could just Google completing the square, look, a million things will pop up, and you can get some more review on it. But we're going to need this to manipulate functions so we can make them easier for us to integrate. Here's an example where we're going to need that completing the square. So first thing I want to look at is integrating this function. We don't really have a lot of options. We can't do a simple u substitution because we don't have a du. I mean, the only logical thing to let u be would be the denominator, and the derivative of that would be 2x minus 4. You don't see that anywhere, so that's out. There will be a couple options later down the line when we learn more integration techniques, but we're really limited right now in what we can do. So what we're going to do here is noticing we have this quadratic trinomial here. So if I look at this fraction, 1 over x squared minus 4x plus 7. And I want to rewrite this in a different way so that I can integrate it. Well, what I'm going to do is I'm going to work with the trinomial. So if I have x squared minus 4x plus 7, I want to work with this piece here, similar to the last example I just gave. I mean, we basically did the same thing. I want to complete the square here. So if I look at this, I have a 1 in front of the x squared. I take this and I'm going to divide it by 2, which is going to give me negative 2. So I have x squared minus 4x plus negative 2 squared. Now if I added negative 2 squared, I'm also going to subtract negative 2 squared. And then I still have the plus 7. In the previous example, this was a plus 4, but it doesn't really matter whether it's positive or negative. You work it the same way. So then we look at this here. So what happens here is that this is going to end up being x minus 2 squared, and that's where the big difference is because of the minus here. Here we're going to have a minus 4 plus 7, so we're going to get 3. And so I'm going to rewrite it like this. So now this is the same thing as 1 over x minus 2 squared plus 3. And so how is this helpful? Well, it's helpful in that it'll allow us to integrate this using the arctan function. So if I have dx over x minus 2 squared plus 3, if I let a equal square root of 3, so that this is a squared, if I let u equal x minus 2, then this will be u squared, and du would just be dx. So the integral would become du over u squared plus a squared, which is the exact form for arctan. So we would get 1 over a arctan u over a plus c. Where remember a was root 3 arctan of x minus 2 over root 3 plus c. And just like before, you can leave these root 3's in the denominator. We're not going to rationalize those. But you see, by completing the square, we can then switch this into something that can be integrated. Doesn't always work, but this is one little trick to look at. Now, there's something about this. First off, some constant over a quadratic trinomial, one thing you can try is to complete the square. So I gave you an example, in the previous lesson that said just keep this in mind, and here's the reason why. So when you see something like this, an integral like this, think about possibly completing the square. Now, that's not going to be the only way to get this thing done in the long term, but right now it's going to work. Also, when it comes to completing the square, this 7 seems fairly insignificant, but it's not. It's actually very important, because that really affects what's going to happen here, which really affects whether or not this is going to be an arctan integral. Example, let's say that 7 was a 2. Well, if that 7 was a 2, and then we look at this here, this would be minus 4, because this is really 4, right? Negative 2 squared is 4. So a negative 4 plus 2 would make this a negative 2. So now this would actually end up being a minus here. And so you wouldn't have u squared plus a squared. You'd have u squared minus an a squared if we somehow let a be, in this case, say root 2. Now if it's u squared minus a squared, now it's not an arctan integral. Now we're out of luck here. You go, well, maybe it's one of the other ones. No, it can't be one of the other ones because we're missing a square root and a lot of other pieces too. And so this is just showing you that completing the square helped us integrate this example. But there's a lot of things that have to go right for this to work. And so looking at all these pieces, everything has to work out perfectly for us to do this. But it's something you should keep in your tool belt, in that if you see an integral that looks like this example, think about completing the square in that quadratic trinomial denominator to get you to an integral you can work with. Here's an example that talks about the applications of integration, one of which is area, which you remember from Calc 1. Here's a function. Okay, if we were to graph that function, you see it here. That function sits completely above the x-axis, which is nice. It keeps this in area easier. We want to find the area between 3/2 and 9/4. So since this area is completely contained above the x-axis here, we don't have to make any corrections to this area at all. It's just straight look at integrating this function over this interval. And so the area can easily be computed by doing the integral of 1 over the square root of 3x minus x squared dx between 3/2, what's going on there, between 3/2 and 9/4. Now the hard part is doing the integral, but realizing what integral will give you the area should be the easy part, especially if you are looking at the graph. So then the question is, how are we going to do this integral? Well, here's another one where we're going to need completing the square. So let's look at this a little bit closer. I'm going to look at this thing inside the square root. The reason why we need completing the square is we really don't have any other options. If you think about it, the only other real options we have for a lot of these would be substitution. You might think arcsin, but this isn't a constant. If it was 3 minus x squared in that square root, it would be the a squared minus u squared setup, which would be good for arcsin. But it's 3x. And then that changes the fact that it's not a constant, so it's not an a squared, and then we have trouble. All right, so what are we going to do? Well, we're going to look at this. I'm going to rewrite it as minus x squared plus 3x. I just like putting the square out in the front. The one thing I talked about is you have to have a positive 1 out in front of the x squared. We don't. So what I'm going to have to do is I'm going to have to factor out a negative. I'm going to have to write it as x squared minus 3x. Okay. Now I'm going to work with completing the square here. So we talked about take this thing here, divide it by 2, and add it. So if I add negative 3, yeah, this is too small. Let me make it bigger. So if I added negative 3 halves squared to this polynomial, I'll allow me to factor this. Now the problem is I can't just add it, right? I always have to subtract it. Now the problem is I didn't actually add negative 3 halves squared. Negative 3 halves squared, first off, is 9/4. And this negative out here would actually give me an extra negative 9/4. So if I technically have an extra negative 9/4 from what I had to start with, then I have to have an extra positive 9/4 to cancel that out. So now what do I have here? I have this negative outside. For some reason my pen's not working. Give me a second. So negative, this will factor as x minus 3 halves squared. And I have this plus 9/4. And so now we're rewritten this way, which I can actually rearrange one more time, and I'll write this as 9/4 minus x minus 3 halves squared. I'll put this back into the integral. So I have dx over the square root of 9/4 minus x minus 3 halves squared. And then what I'm going to do is substitute. So a will be 3 halves, so that's a squared. U will be x minus 3 halves, so that this is u squared. Du is just going to end up being dx, and I'm going to end up with the integral of du over the square root of a squared minus u squared. And that's your arcsine integral. So we end up with arcsine of u, which is x minus 3 halves, over a, which was 3 halves. And that's going to be between 3 halves and 9/4. So the last part is to plug in these values. And so if we plug in 9/4, we have to do 3 halves minus 9/4, or 9/4 minus 3 halves. And what 9/4 minus 3 halves would give me, well, 3 halves would be 6/4, so it would be 9/4 minus 6/4, so it would give me 3/4. So it would be the arcsine of 3/4 over 3 halves, minus, if I plug in 3 halves, I'm going to get 3 halves minus 3 halves, so it's just 0 over 3 halves, so it's just arcsine of 0. And so here where you see we need to learn we have to know how to evaluate these inverse trig functions. Right now it's starting to come in. Well, if I flip and multiply to get this, what am I going to get? I'm going to get a half, so I have the arcsine of a half, which is pi 6, minus the arcsine of 0, which is 0. So overall I get pi 6. So the area here is pi 6. This last part is just plugging things in and evaluating, and you're going to need that skill. But the big part is all this, right? Completing the square, using that to turn it into an inverse trig, integral, and then integrating. Again, it has to work out perfectly. There's a lot that goes into this that just happens to work out. One of these pieces doesn't quite line up right with the arcsine integral. It doesn't always work. So not something you're going to do all the time, but something you should keep aware of. So again, I'm going to say this same as I said before. Integration is definitely harder than differentiation. There's a lot of tricks, there's a lot of techniques that we need to still learn as it relates to integration, but this is a list of 20 integrals that you should know. We've gone over this already when we reviewed integration in the beginning of the semester, but these are the 20 integrals that you should know. And I highly suggest you make flashcards, put this on one side of the flashcard, put the answer on the other side. Pause the video to look at all these integrals here. But these are all the integrals that you should know at this point. And the new ones here are the ones you should probably have to spend the most time on because we just learned them. We still have a lot of integration we have left to learn. And the problem with integration is it's not as straightforward as differentiation. When it comes to derivatives, you just have to know what type of function you're dealing with, and there's a rule that tells you this is how I take the derivative. And just straightforward, apply the rule, get the answer. Integration is not so easy. Integration, while you have a set of rules that you work off of, integrations are more like a puzzle, and you have to figure out how do these rules fit into that puzzle. And use substitution is a primary way we kind of make that happen. But like you saw, completing the square is one little trick we can use to make these rules work. And there's a whole lot of integration techniques we still have yet to learn. So here's an example of why integration can be tricky. Here are 3 integrals. They all look very similar. Slight tweaks. This has an x in the denominator. This has that same x but in the numerator. And this one is remove the x altogether. Those slight differences make a huge difference in terms of how we're going to integrate each one. And so when we go through to try and integrate each one of these functions, we need to think about all the things we've learned. Now, the major technique you've learned so far is substitution. And so we use substitution as a means of turning these integrals into one of the most basic 20 integrals that I just showed you previously. And so let's look at this first integral. If I look at this, I have to have an idea of kind of where I think I should go with this. And right off the bat, this one starts to look like it has the form for the arcsecant. We have the subtraction in the right order. We have the extra x outside the root. So I'm going to try and turn this into an arcsecant integral. I'm going to do that by saying a equals 1, u equals x. Therefore, here we see u squared minus a squared. This is u squared minus a squared. And then that would make du equal just dx. And so everything's there perfectly in that we have du over u square root of u squared minus a squared. Okay? And you might not even need to do this substitution to realize what the answer here for this integral is because it is so basic. And we end up with 1 over a, which would be 1 over 1, arcsecant of u over a, which is x over 1. I don't know why my computer's going crazy. X over 1 plus c. And so you don't have to write all this 1 over 1 business, so just arcsecant of x plus c. Very simple. You put the absolute value on the x. Okay, don't forget that piece. Which is really only important necessarily when we're doing a definite integral. Something we should talk about. This absolute value is important when x is evaluated. And so if we were doing, say, a definite integral, and we had to, say, evaluate it between 5 and 7, well, the absolute value doesn't need to be there because the absolute value of 7, absolute value of 5 would be the same thing as just not having the absolute value. But let's say our interval was -2 to 3. Well, now there's a series of x's where that absolute value is going to matter. And so the absolute value really only plays a role when we're doing definite integrals for this. All right. Let's look at the next example. Totally different. By moving that x to the numerator, this changes completely how we're going to do this integral. This is not going to be an arcsine integral. Now we're going to use substitution, but we're going to simply let u equal that entire radicand inside the root. Reason being, if I say du is 2x dx, I have the x dx sitting right here. By moving that x to the numerator, I now have a du sitting up there in the numerator. Now, the 2 is the problem, but we know we can move that 2 over. And so what I end up with here is du over 2, which I'll pull the 1/2 out to the front, over just the square root of u. Well, that's the same thing as 1/2 du over u to the 1/2, which is just going to be a power rule integral. I'll bring the 1/2 up, so negative 1/2. So one of the most basic integrals you can do is a power rule integral. And then I am going to add 1 to that power, which would be 1/2. I'll divide by that, which really means I'm going to multiply by 2. U was x squared minus 1. Throw plus c on there. These two 2's cancel. So I get x squared minus 1 to the 1/2 plus c. Very different answer than we got over here, simply by moving the x from the denominator to the numerator. That, again, that's why integration is so tricky. Two integrals look very, very similar. Slight difference makes all the difference. Now we look at this last one. Well, the technique from the first one isn't going to work because I don't have the x out here, so I can't make it turn into an arcsecant. The technique from the second one is not going to work because I don't have the extra x here, so I can't use this substitution. So then the question is, well, what am I going to do? Well, the subtraction is wrong for arcsine. And so you try and go through all your lists. Maybe I say, let's try and, complete the square. That's not going to work because I'm missing the x to the first power. So what am I going to do? Well, it's kind of a trick question. Right now, nothing. You can't integrate this one using the techniques and the rules that we've learned so far. So this is showing you that what looks like a fairly simple integral, you still don't know how to do. We still have a lot of integration we need to learn. And that's really the whole second unit of this semester is going to be all about learning these different ways of integrating. And so we're going to come up with something called trigonometric substitution. That's going to be the best way to attack this thing. This one, probably of the three integrals, looks the simplest, but that's also what makes it the hardest, in that there's less to work with. The more there is to work with in an integral, the more options you have in terms of what you can do with it. The simpler the integral looks, the less options you have to work with, and therefore it could make it a little bit difficult. So right now, this one is to be continued, and we'll pick up with that when we get to something called trigonometric substitution. Here's three more integrals. Again, they look fairly similar. Now these are a little bit, more different than the previous three. I'm moving things around a little bit more, but generally it's the same idea. Here I have the log in the denominator. Here I move that log to the numerator. I still have the dx and the x, but that's the difference between these two. And this one, I removed that x altogether from the denominator. I just got rid of it, and I have this. So let's look at all three. Now these three are going to be a little bit more similar than the previous three were in that u substitution across the board. We're going to use basically the same u substitution for the first two, in that u would be log x, and du is going to be 1 over x dx. That's going to work for both d and e, but the integrals that result are different. And the reason why I do that is, and it's kind of going to lead into this one, is that when it comes to doing logarithms, we have learned to differentiate a logarithm. That's what we did here. We actually haven't integrated a logarithm yet. It's kind of foreshadowing this integral here. And I'll talk about that more in a second. So let's look at these two. The reason why I chose that substitution, just because it works. So if I let this be u, then dx over x is what's left. But if you look at this, dx over x is exactly what du equals. So I end up with du over u for this integral. Well, du over u is the exact setup for a logarithm integral. So that would be log of the absolute value of u plus c. And therefore, I would have log of the log of x plus c. I should have the absolute values there. Okay? And so there's the answer for that first integral. If you look at the second integral, same substitution. Here's your u, and here's a dx over x. That's your du. But what results is we end up with u du instead of du over u? Well, that's just u to the first, which is a power rule integral. And so we'd have u squared over 2 as our integral. And so we get log x all squared over 2 plus c as our answer there. But very different answers because of where that logarithm sets up, because we end up with a power rule integral versus a logarithm integral. Now, that leads us into this one. I said we have not integrated a logarithm. We've done the integral where the answer is a logarithm, but we haven't actually integrated a logarithm directly. It's one basic function that we don't know the integral of. Okay, we've done the integral of exponentials, trig functions, but we haven't directly integrated a logarithm. And we don't know how to do that right now is the reason why we haven't done it yet. We're going to need a technique called integration by parts to get that done. And so this one, again, you don't know how to do yet. Think about some other basic functions we haven't integrated yet. We haven't done the integral of, say, arcsine. We haven't done the integral of arctan or arcsecant. You might say, well, we just got done doing that. No, what we did was the integral where the answer, the integral of du over the square root of a squared minus u squared, where the answer is the arcsine of, let's say, u over a. Okay, but we haven't actually integrated an arcsine itself. And so this is what we're going to need integration by parts for, which again is another technique, which just brings home the idea that there's still a lot of integration that we don't know and we still need to learn.